Everything in this video is only imagination. If you have your own ideas, please share them in the comments. Now let's jump into a future where tanks no longer resemble the steel beasts we know today. This video, we explore a vision of future armored warfare that blends speculative engineering with the rapid technological advancements shaping modern defense systems. As military environments evolve faster than traditional platforms can adapt, the concept of a future main battle tank becomes more than just an upgrade to existing vehicles. It represents a rethinking of what a tank fundamentally is, how it moves, how it survives, and how it interacts with the dynamic battlefield. The foundation of tank design has always been simple: combine firepower, protection, and mobility into a single platform capable of dominating ground combat. But the world no longer operates on the assumptions that define 20th century warfare. The rise of autonomous systems, next-generation drones, advanced sensors, precision munitions, and electronic warfare demands a tank that is not just stronger, but smarter, more efficient, and far more adaptable. Future tanks could incorporate materials that behave differently under stress, engines that operate quietly with minimal thermal signature, and onboard intelligence powerful enough to analyze an entire battlefield in real time. They may not rely on the traditional silhouette of a heavy, tracked vehicle pushing forward through overwhelming force. Instead, they could become agile, intelligent platforms capable of participating in a networked ecosystem where information, prediction, and speed matter just as much as armor. The concept of a future tank also invites us to rethink the relationship between humans and machines. Will crews still sit inside these vehicles, or will distance, autonomy, and AI make human presence optional? Will energy weapons replace conventional cannons? Will camouflage become so advanced that the tank itself disappears from sight? These questions guide our exploration, not as definitive predictions, but as a creative framework built from emerging technologies already in development today. What you're about to see is not a blueprint or a leaked prototype. It is an imagined evolution based on scientific trends, engineering possibilities, and the challenges modern militaries face as warfare accelerates into an era shaped by data, automation, and high-precision threats. As we dive deeper into material science, propulsion ideas, weapon innovations, and intelligent defense systems, think of this video as a conceptual journey into what tomorrow's armored machines could become if technology continues to advance at its current pace. Everything remains hypothetical, yet firmly grounded in real research and ongoing experiments across the world. This introduction sets the stage for a detailed look into a future where the tank is transformed from a heavy metal vehicle into an adaptive, multifunctional system designed for a battlefield defined by speed, uncertainty, and constant technological evolution. The tanks of today are the product of design philosophies shaped by conflicts from decades past. Thick armor, large caliber cannons, diesel engines, and visible silhouettes have worked for a long time, but warfare has changed into something far more complex than direct armored confrontation. Modern battlefields are saturated with drones capable of tracking and striking targets from above, guided munitions that can identify and adjust mid-flight, electronic warfare systems that disrupt communication and GPS, and surveillance tools that detect heat, sound, and electromagnetic signatures. Because of this, future tanks can no longer rely on mass and brute force as primary survival tools. They must become harder to detect, faster to reposition, and smarter in how they interpret threats. What once was a straightforward metal giant must now be a sophisticated blend of sensors, algorithms, and adaptive technologies. Another factor reshaping future tank design is the shift from platform-centric to network-centric warfare. Instead of fighting as isolated units, tanks of the future will operate as nodes within a larger digital ecosystem. Every movement, every sensor reading, and every environmental change can be shared instantly across a battlefield network. This means future designs must prioritize data processing, communication resilience, and the ability to identify threats long before they appear visually. Furthermore, advancements in material science push the idea of physical armor beyond traditional steel and composite plates. Engineers are exploring substances that react to energy, reshape under impact, or recover after taking damage. These changes will dramatically alter the look and structure of a tank's exterior, favoring modular, flexible surfaces over rigid armor. Propulsion also plays a major role in redefining the silhouette and internal layout. New engine concepts produce less heat and noise, allowing for compact designs and unconventional shapes optimized for stealth rather than raw engine space. Even the tracks or wheels could evolve, enabling new forms of locomotion that help the machine adapt to unpredictable environments. Finally, the role of human operators is shifting. As artificial intelligence becomes more capable, it may take over critical decision-making functions, transforming the crew from direct controllers to strategic supervisors. This change influences everything from interior design to overall vehicle size, potentially removing the need for large compartments dedicated to human safety. All these factors combined point to a future where tanks are not merely improved versions of today's machines, but entirely new forms shaped by the demands of information warfare, stealth requirements, and rapid response scenarios. The armor systems envisioned for future tanks represent one of the most dramatic departures from today's conventional protective technology. Traditional armor relies on thickness, layers, and specialized materials designed to absorb or deflect kinetic energy. While effective in past conflicts, this approach reaches its limits in a world where hypersonic penetrators, top-attack drones, and precision-shaped charges continue to evolve. Instead of merely resisting incoming fire, future armor systems must respond to it dynamically, adapting to the nature of each threat in real time. One of the most intriguing concepts is the use of nano-engineered alloys. These materials are structured at the microscopic level, allowing them to rearrange their internal bonds or molecular geometry when subjected to stress. When a projectile impacts the surface, the alloy doesn't simply break or deform in a predictable way. It actively redistributes energy, causing the force of the strike to dissipate across a broader surface area. This drastically reduces penetration and prevents catastrophic internal damage. In many theoretical models, such materials can even heal over time, slowly returning to their original structure through controlled thermal or electrical stimulation. The idea resembles biological tissue repairing itself, except accelerated through engineered chemistry. Another emerging vision centers on electromagnetic armor. Here, the tank's outer shell is connected to a high-capacity energy system capable of releasing extremely rapid electrical pulses. When a shape-charged jet or penetrator strikes, the system activates instantly. The electrical discharge interferes with the stability of the incoming threat, either weakening the formation of a metal jet or destabilizing a kinetic rod. Instead of relying on physical mass, this form of protection uses energy and timing as its primary tools. Although still theoretical, prototypes of electromagnetic reactive armor have been discussed in research circles for years, and advances in compact power systems make the idea more feasible each decade. Beyond physical and electromagnetic responses, conceptual designs also explore the possibility of plasma-based defensive layers. Plasma is superheated, ionized gas capable of disrupting matter and energy passing through it. In theory, a tank could generate a thin plasma sheet around its surface during high-risk moments. This would not behave like a sci-fi force field, but more like a rapidly generated, incredibly hot haze that weakens incoming munitions by altering their structure or slowing them with intense energy resistance. While extremely power-hungry and technologically difficult, plasma shielding represents the outer edge of speculative armor research, pushing the idea of protection into the realm of controlled energy physics. Modular armor is yet another critical evolution. Instead of a single body of armor fixed to the hull, future tanks may use exterior surfaces composed of independent panels that attach magnetically or mechanically. Each panel could contain specialized materials, some designed for kinetic threats, others optimized for thermal or electromagnetic attacks. If a panel is damaged, it can be detached and replaced quickly in the field, reducing repair time and increasing survivability. Modular designs also allow the tank to configure its protection depending on the mission, adding heavier panels in urban environments or lightweight versions in reconnaissance roles. Sensors integrated directly into the armor add another layer of intelligence. These embedded systems continuously analyze the surrounding environment, monitoring heat signatures, vibrations, radar reflections, and acoustic patterns. When the armor detects an incoming threat, it sends data to the tank's internal AI, which then determines the best defensive response. This might include reorienting armor plates, triggering countermeasures, or adjusting the tank's posture to reduce exposure. Finally, some futuristic concepts explore adaptive surface technologies capable of slightly reshaping or reconfiguring themselves. Using flexible composites, micro-actuators, and responsive materials, the armor could adjust angles or curvature to deflect incoming fire more effectively. Even slight changes in angle can drastically reduce penetration potential, turning a direct hit into a glancing strike. This type of morphing armor marries physical protection with mechanical agility, offering a level of versatility no current platform possesses. Taken together, these systems represent a future where armor is no longer passive and static. Instead, it becomes active, intelligent, and responsive, behaving more like a living ecosystem of materials, sensors, and energy fields working in harmony. Future tanks will not rely solely on thickness or weight. They will survive by outsmarting threats, adapting to new forms of attack, and using advanced physics to maintain battlefield dominance. The future engine, silent, efficient, almost unstoppable. The engine systems envisioned for future tanks represent one of the most fundamental shifts in armored vehicle engineering. Traditional tanks rely on massive diesel or turbine engines, generating enormous heat, significant noise, and large electromagnetic signatures. These characteristics make them vulnerable to modern detection systems, especially drones and thermal imaging. The future battlefield demands a new approach, one where mobility is not just about power, but about stealth, efficiency, and the ability to operate in environments where traditional engines simply cannot survive. This new form of propulsion must combine raw output with subtlety, merging high performance with near invisibility. One of the leading concepts is magnetic propulsion, using high-strength superconductors to generate rotational force with minimal friction. Unlike combustion engines, magnetic systems rely on controlled electromagnetic fields to move internal components. This means fewer moving parts, drastically lower heat production, and almost complete silence during low-speed operations. Such engines could allow a tank to maneuver quietly across terrain, positioning itself without revealing its location to enemy sensors. Magnetic propulsion also offers exceptional torque, enabling vehicles to climb steep inclines, accelerate rapidly, or maneuver in tight, uneven spaces that traditional tracks struggle with. Complementing magnetic propulsion is the rise of solid-state energy storage. Future tanks may incorporate high-density battery arrays using advanced materials like graphene composites or solid electrolytes. These systems can store massive amounts of energy in relatively compact volumes, creating a power source that is both durable and resilient. Battery-based propulsion eliminates exhaust, reduces thermal signatures, and allows for prolonged silent movement. The challenge lies in balancing weight, energy density, and recharge rates, but continuous advancements in civilian electric vehicle technology make this pathway increasingly realistic. Tanks equipped with such batteries could remain stationary for extended periods while maintaining full operational readiness, something nearly impossible with today's idling engines. In some concepts, these battery systems are paired with microturbines that function as onboard generators. Instead of powering the tank directly, the turbines simply recharge the battery array as needed. These microturbines operate more efficiently than large engines, producing less detectable heat and noise. They also allow the tank to operate in hybrid mode, switching between silent electric movement and boosted turbine-assisted power when speed or heavy maneuvering is required. Hybrid propulsion not only increases operational flexibility, but also extends the vehicle's range significantly, reducing reliance on fuel convoys that often become vulnerable targets on the battlefield. Adaptive suspension systems form another crucial part of future mobility. Instead of static shock absorbers and fixed track tension, next-generation suspensions may use magnetorheological fluids or electrically controlled actuators capable of adjusting stiffness, height, and responsiveness in real time. This allows the tank to lower its profile during stealth approaches or raise itself to clear obstacles. A lowered profile reduces radar cross-section and visual silhouette, making the tank harder to detect. Meanwhile, an elevated stance assists with climbing rubble, debris, uneven hillsides, or even vertical surfaces when paired with advanced adaptive tracks. Speaking of tracks, future designs may incorporate modular track systems that can reconfigure themselves depending on terrain. On soft ground, they could expand contact surface for better traction. In urban environments, they might tighten to improve agility. Some futuristic concepts even propose hybrid track wheel systems, where sections of the track can act as independent wheels for smooth surfaces, allowing higher speeds and more efficient movement. These adaptive tracks could use embedded sensors to detect terrain conditions and optimize performance automatically, reducing driver workload and improving survivability in unpredictable environments. Thermal management also becomes a strategic component of engine design. Instead of radiators and exhaust vents, which reveal the tank's location, future engines may rely on distributed heat sinks, phase change materials, or energy redirection systems that absorb or reroute excess heat. This allows the tank to operate for longer periods without revealing its position to thermal imaging systems. Some concepts even propose directing heat into batteries or armor panels, where it can be stored temporarily or dissipated gradually in a controlled manner. Ultimately, the future engine transforms the tank from a loud, heat-heavy machine into a stealth-capable platform with extraordinary mobility. The combination of magnetic propulsion, advanced batteries, hybrid generators, adaptive suspensions, and intelligent thermal systems creates a vehicle that moves not like a traditional armored giant, but like a silent predator, capable of surprising its opponents. These innovations redefine mobility itself, making the tank not just faster or stronger, but nearly impossible to track, predict, or stop. The weapons systems envisioned for future tanks go far beyond traditional cannons and machine guns. As warfare shifts toward faster engagements, smarter munitions, and multi-layered threats, future tanks must deliver firepower that is precise, adaptive, and devastating across multiple ranges. The primary weapon of tomorrow's tank is often imagined as a railgun, a system that uses electromagnetic force rather than chemical propellants to launch projectiles. Instead of relying on an explosion to propel a shell, a railgun accelerates a solid metal slug down a pair of conductive rails using controlled magnetic fields. This results in muzzle velocities far greater than anything conventional cannons can achieve. At such speeds, kinetic energy alone becomes the destructive factor, allowing even relatively small projectiles to penetrate armor, disable vehicles, or destroy fortified positions with exceptional accuracy. The absence of explosive propellant also reduces logistical strain, makes ammunition safer to store, and enables the tank to carry more rounds. Railguns, however, are just the beginning. Many conceptual designs incorporate energy weapons as secondary armament. High-energy laser systems are particularly promising due to their precision, speed of light engagement, and versatility. Unlike kinetic weapons, lasers don't arc, travel, or require physical ammunition. They deliver destructive thermal energy instantly. On the modern battlefield, drones, sensors, and guided munitions pose serious threats. Future tanks equipped with turret-mounted laser arrays could neutralize these threats long before they reach effective range. A laser can slice through the wing of a drone, disable a camera system, ignite explosives, or sever communication lines with pinpoint accuracy. These systems also excel at silent engagements, providing the tank with a covert method of eliminating reconnaissance assets without giving away its position through sound or muzzle flash. Missile technology is also expected to evolve significantly. Instead of large, bulky missiles, future tanks may rely on compact, intelligent micromissiles capable of adjusting trajectory mid-flight, identifying targets using onboard sensors, and coordinating with other missiles in a swarm. These weapons could strike from above, curve around buildings, dive at precise angles, or adapt to moving targets in real time. Because they are small and numerous, the tank gains a wider tactical envelope, allowing it to engage infantry, vehicles, drones, and heavily armored opponents with incredible flexibility. Swarm tactics become particularly important. A tank might launch a pack of autonomous mini-drones that scout ahead, identify enemy positions, jam communications, or even deliver small explosives with surgical precision. Internally stored drone swarms represent one of the most radical additions to future tank armaments. Instead of relying solely on onboard weapons, the tank becomes a mobile command hub for coordinated drone operations. These drones could be air-based or ground-based, each equipped with sensors, cameras, decoys, or low-yield charges. Some drones may function purely as reconnaissance tools, mapping terrain and highlighting hidden threats. Others could carry electronic warfare modules, disrupting radars or intercepting signals. A specialized strike drone could attach itself to vulnerable enemy systems and detonate at the optimal moment. By decentralizing offensive power, the tank becomes an entire ecosystem of offensive capability. Autonomous fire control systems integrate these weapons into a unified network, managing sensors, threat prioritization, and attack timing. Instead of the crew calculating trajectories or adjusting aim manually, AI analyzes environmental factors, enemy patterns, wind conditions, and heat signatures in milliseconds. The tank's weapons do not operate in isolation, but in harmony, selecting the best tool for each situation. For instance, a drone swarm may detect an incoming missile, prompting the tank to use a laser to disable it while simultaneously preparing the railgun for a counterattack against the launcher. The tank becomes something far more advanced than a simple gun platform. It becomes an intelligent, multi-layered offensive system capable of dominating complex environments. These future weapons redefine how tanks interact with the battlefield. They combine extreme range, rapid engagement, precision targeting, and intelligent coordination. Instead of overwhelming force alone, the tank leverages speed, data, and adaptability. Every tool, from hypersonic railgun rounds to laser bursts to autonomous drones, works as part of a strategy designed to overcome modern threats. In this vision, firepower is not just about destruction. It is about control, timing, and shaping the battlefield in ways that were impossible for earlier generations of armored vehicles. Artificial intelligence is arguably the most transformative component in the vision of future armored warfare. Unlike armor, engines, or weapons, which enhance specific aspects of a vehicle's performance, AI has the potential to redefine the very nature of how a tank operates. It shifts the machine from a human-driven tool into an autonomous decision-making platform capable of reacting, planning, and executing tasks with a level of speed and precision no human crew could match. At the core of this transformation is the integration of advanced neural networks designed to analyze enormous streams of battlefield data in real time. Modern combat environments produce overwhelming volumes of information, from drone feeds and radar signatures to acoustic patterns and electronic signals. A tank equipped with next-generation AI systems can process these inputs instantly, identifying threats, mapping positions, predicting enemy behavior, and recommending or executing countermeasures before a human operator would even recognize the danger. One of the most profound implications of AI integration is the shift from manual control to collaborative autonomy. Instead of the crew directly steering, aiming, or navigating, the tank's AI manages most operational tasks. Human operators become supervisors rather than drivers or gunners. They monitor systems, manage mission-level decisions, and override the AI only when necessary. This relationship dramatically reduces the cognitive burden placed on the crew while allowing the machine to operate at peak efficiency. When milliseconds matter, the tank does not wait for human reaction times, it simply acts. Whether adjusting armor orientation, intercepting incoming fire, or choosing optimal routes through complex terrain, AI ensures the vehicle always performs with maximum situational awareness. Another crucial advantage lies in predictive analytics. Traditional tanks rely on sensors that detect threats as they occur. Future AI-driven systems go a step further, predicting threats before they materialize. Using pattern recognition, environmental modeling, and historical combat data, the AI can forecast where enemy anti-tank teams might position themselves, which drones pose the highest likelihood of attack, or which routes are statistically safest. This proactive behavior turns the tank from a reactive platform into a strategic participant capable of shaping its own survivability and combat effectiveness. AI also revolutionizes the way weapons are deployed. Fire control systems equipped with machine learning algorithms can track multiple moving targets simultaneously, compensating for range, wind, velocity, and environmental interference with unparalleled precision. When combined with autonomous drones, the tank becomes a command center capable of orchestrating multi-vector attacks. The AI might launch reconnaissance drones to identify enemy armor, dispatch strike drones to neutralize exposed units, and coordinate railgun fire to eliminate fortified positions. These operations occur in a seamless, synchronized flow, guided by algorithms that prioritize efficiency and mission success. The evolution toward full autonomy raises an important question. Will future tanks even require human crews? In high-risk environments contaminated by radiation, chemical hazards, or extreme temperatures, AI-driven unmanned tanks offer clear advantages. Without the need to protect human life inside the hull, the vehicle can be smaller, more maneuverable, and more resilient. It can take risks no crewed platform could justify. Fully autonomous tanks could operate in coordinated clusters, forming intelligent armored swarms that communicate instantly, reposition fluidly, and respond to changing battlefield conditions with algorithmic precision. Each tank acts as both an independent unit and a node within a larger collective intelligence, sharing data and coordinating actions more efficiently than traditional human-led formations. At the same time, ethical and strategic considerations suggest humans may remain involved in high-level oversight. The hybrid approach, where AI operates tactically but humans maintain final authority over lethal decisions, is likely to dominate early generations of autonomous tanks. This ensures accountability and prevents unintended escalation while still harnessing the immense power of artificial intelligence. In this envisioned future, AI becomes the nervous system, brain, and reflexes of the armored machine. It transforms the tank from a vehicle into a living digital organism, constantly learning, adapting, and improving. With AI at the helm, tanks no longer rely solely on thick armor or overwhelming firepower. They survive and succeed because they can think faster, act sooner, and outmaneuver threats in ways no traditional platform ever could. Cloaking and camouflage technologies imagined for future tanks represent some of the most visually striking and conceptually revolutionary elements of next-generation armored design. In modern warfare, being seen is often equivalent to being targeted, and being targeted by advanced guided munitions frequently means being destroyed. As threats become faster and more precise, survivability depends not only on armor or speed, but on the ability to avoid detection altogether. Future tanks may achieve this through a combination of optical camouflage, thermal masking, electromagnetic signature reduction, and adaptive surface technologies that work together to create an almost ghost-like presence on the battlefield. One of the most intriguing concepts is adaptive optical camouflage. Unlike static paint or netting, this system uses a network of high-resolution display panels integrated directly into the exterior surface of the tank. Cameras positioned around the vehicle continuously capture the surrounding environment from every angle. The captured imagery is then processed and displayed on the tank's surface, effectively turning the vehicle into a moving projection screen. When done with sufficient resolution, color accuracy, and lighting adjustment, the tank appears to blend seamlessly into the background, becoming nearly invisible to the naked eye. This technology, sometimes referred to as active camouflage, behaves similarly to the adaptive skin of cephalopods like octopuses and cuttlefish, but at a much more advanced technological level. Thermal camouflage forms the second critical layer. Modern detection systems rely heavily on infrared signatures to locate targets at long distances. A traditional tank, with its roaring engine and hot exhaust, produces a thermal footprint that is easy to track even through dense smoke, darkness, or vegetation. Future tanks will likely use advanced thermal dispersion systems that distribute heat evenly across the surface, lowering hotspots and reshaping the thermal pattern to resemble background elements. Some concepts propose flexible heat-absorbing tiles filled with phase-change materials that temporarily store heat and release it slowly over time. Others envision microfluidic cooling networks woven throughout the armor, pumping coolant to specific hotspots to keep the thermal profile flat and undetectable. In combination, These technologies not only reduce the tank's infrared signature, but can make it appear as if it is not emitting heat at all. Beyond optical and thermal stealth, electromagnetic signature reduction is becoming increasingly important. Many modern surveillance systems detect tanks through radar reflections or electronic emissions from their sensors and communication equipment. Future tanks may use radar-absorbent materials, electrically controlled surface coatings, and low-profile antenna systems to minimize or distort radar signatures. Some designs even incorporate smart surfaces that can change texture or shape to disrupt radar waves, scattering them unpredictably rather than reflecting them back. By manipulating electromagnetic properties, the tank becomes far harder to identify on enemy radar screens, blending into background clutter or appearing as an innocuous object. Another groundbreaking idea involves structural metamaterials, engineered surfaces that manipulate light, heat, or electromagnetic waves in ways natural materials cannot. These metamaterials could bend incoming light around the vehicle, creating a primitive form of invisibility where the tank appears to warp or distort the space behind it. While still in early experimental stages, metamaterial-based cloaking represents one of the most promising avenues for long-term stealth development. If perfected, such technology could dramatically alter battlefield visibility, allowing armored vehicles to move through contested zones without triggering early detection systems. Adaptive surfaces complete the stealth package. These surfaces may use micro-actuators to change the tank's physical texture, allowing it to mimic natural or urban structures. On rocky terrain, the armor could extend rough patterns to match surrounding stones. In forests, it could adopt a bark-like texture. Combined with optical projection, the result is an illusion that goes beyond simple visual blending and becomes immersive environmental mimicry. When a tank can not only display the colors of a tree line, but also mimic its shadows and textures, it becomes extraordinarily difficult to distinguish from the environment, even at close range. Together, these cloaking and camouflage systems allow the future tank to navigate dangerous landscapes without necessarily engaging threats. Instead of fighting through detection, the tank avoids it entirely, gaining the strategic advantage of surprise. In a world where precision-guided weapons and autonomous drones can strike with near-perfect accuracy, the ability to remain unseen may become the most effective form of protection. The battlefield of the future will not resemble the predictable environments where tanks have historically operated. Instead of open plains, desert expanses, or dense urban grids, tomorrow's combat zones may include flooded coastlines, radioactive wastelands, polar ice sheets, underground transit networks, megastructure interiors, and landscapes reshaped by climate extremes. As warfare expands into domains that challenge human endurance and mechanical reliability, future tanks must evolve into versatile platforms capable of surviving and performing in environments far beyond the limitations of today's armored vehicles. One of the most compelling concepts is amphibious or semi-submersible capability. Traditional tanks struggle with deep water, relying on snorkels or limited amphibious adaptations that often compromise speed and stability. Future tanks, however, may incorporate sealed hulls, ballast control systems, and water jet thrusters that allow them to travel underwater for short distances. This capability would enable stealth crossings beneath rivers, canals, or coastal inlets, bypassing predictable choke points and striking behind enemy lines without detection. Underwater traversal would also grant tanks access to subterranean tunnels, service channels, or collapsed infrastructure that conventional vehicles cannot reach. Extreme cold environments pose another major challenge for today's armor. Ice, snow, and permafrost can immobilize heavy vehicles, freeze lubricants, and reduce sensor performance. Future tanks may integrate advanced heaters, self-warming materials, and cold-resistant composite structures designed to maintain flexibility and mechanical integrity even at temperatures far below freezing. Adaptive track systems could alter surface patterns to provide traction on ice, while distributed weight systems prevent the vehicle from breaking through fragile ice sheets. In polar or alpine battlefields, such innovations would allow tanks to maneuver in silence across frozen terrain, using the environment itself as cover from thermal and acoustic detection. Urban warfare will continue to evolve as cities grow more complex, dense, and technologically interconnected. Future tanks must navigate narrow corridors, collapsed structures, multi-level platforms, and confined indoor spaces. To meet these demands, conceptual designs incorporate compact chassis options, rotating track assemblies, and articulated hulls capable of bending slightly to navigate tight angles. Some ideas even propose retractable modules that reduce the tank's width, allowing it to slip through alleys or damaged infrastructure that would block conventional armor. Advanced 3D mapping systems using LiDAR, radar, and thermal imaging allow the vehicle to construct real-time interior maps, identifying ambush points long before they pose a threat. Dust storms, volcanic ash clouds, and chemical contamination represent further environmental obstacles. Instead of relying on filtered air intake systems that can clog or fail, future tanks may use sealed internal air circulation with regenerating filters and atmospheric processors that clean or recycle air. Sensor arrays strengthened with multi-spectrum redundancy ensure visibility even when optical modes fail. Radar and thermal systems compensate for dust or debris, while onboard AI analyzes patterns to identify hidden threats through layered interference. Underground and enclosed environments also form part of the battlefield of the future. Tunnels, subway networks, mining shafts, and underground bunkers require vehicles that can operate with minimal GPS, limited maneuver space, and restricted sensory feedback. Future tanks may incorporate omnidirectional wheel-track hybrids that allow lateral movement, vertical climbing on reinforced surfaces, or precise turning in tight spaces. High-frequency acoustic sensors could replace GPS networks, allowing the tank to navigate by analyzing echoes and structural reflections, much like a digital form of echolocation. Multispectrum sensing plays a critical role in these environments. Instead of relying solely on infrared or visible light, future tanks might combine millimeter wave radar, hyperspectral imaging, ultrasonic mapping, and electromagnetic analysis to create an all-conditions vision system. This allows the tank to see through fog, smoke, darkness, debris clouds, or harsh environmental distortions. Whether operating in a blizzard, a wildfire zone, or the aftermath of a collapsed building, the vehicle maintains complete situational awareness. Finally, the ability to adapt to rapidly shifting environments becomes essential. A future battlefield may include dynamic hazards such as rising floodwaters, moving sand dunes, collapsing urban structures, or sudden electromagnetic disruptions. AI-driven terrain adaptation enables the tank to analyze geological stability, water flow patterns, or atmospheric changes in real time. Instead of reacting to obstacles, the tank predicts them, adjusting speed, posture, and trajectory to navigate safely through volatile landscapes. In this vision, future tanks are not limited by the environment, they conquer it. Through advanced propulsion, AI-driven navigation, multispectrum sensors, and adaptive physical systems, they extend armored warfare into domains previously inaccessible to any mechanized force. This expansion of capability transforms the tank from a ground-bound combat vehicle into a truly all-terrain, all-weather platform ready for the unpredictable battle spaces of tomorrow. The defensive systems imagined for future tanks represent a complete rethinking of how armored vehicles survive on a battlefield flooded with precision munitions, autonomous drones, and high-speed penetrators. Traditional passive armor alone can no longer guarantee survival. Instead, next-generation tanks will rely on layers of intelligent defense systems that detect, interpret, and counter threats before they ever reach the hull. These defenses form an interconnected shield of sensors, algorithms, and rapid response mechanisms designed to make the tank extraordinarily difficult to hit, let alone destroy. At the core of this defensive evolution is a highly advanced sensor network capable of monitoring the environment in all directions and across multiple spectrums. Conventional radar and infrared sensors are augmented by hyperspectral scanners, acoustic arrays, millimeter wave radars, laser detection systems, and electromagnetic field monitors. These sensors feed data into a centralized AI processor that continuously evaluates the battlefield. The AI identifies patterns associated with incoming projectiles, such as the unique acoustic signature of a rocket motor, the radar profile of a loitering drone, or the thermal spike of a missile launch. Instead of waiting for a confirmed hit, the AI detects the intent of an attack, predicting trajectory and danger level within milliseconds. Once a threat is identified, the tank deploys its active protection systems. These systems form the first defensive ring using interceptors, directional explosives, lasers, or electromagnetic pulses to stop incoming threats midair. Some conceptual designs imagine a compact, turret-mounted railgun or coil gun specifically dedicated to shooting down incoming projectiles. Others propose high-speed interceptor drones that launch instantly from hidden compartments, intercepting enemy drones or guided munitions before they lock onto the vehicle. A more experimental approach involves directed energy weapons that fire concentrated laser bursts to melt, blind, or destabilize incoming threats before impact. These lasers operate silently, leaving no visible signature apart from a faint atmospheric shimmer. In addition to intercepting threats, future tanks may also use electronic warfare as part of their defensive suite. Jamming signals, spoofers, and electromagnetic disruptors can interfere with the guidance systems of enemy missiles or drones, causing them to lose lock or veer off course. The tank's AI coordinates these electronic countermeasures with its physical intercept systems, ensuring that each threat is met with the most efficient response. For example, a low-cost drone swarm might be neutralized using electronic jamming rather than kinetic fire, allowing the tank to conserve resources for more dangerous threats. Another layer of defense involves dynamic armor configuration. Unlike static armor plates, these systems use micro-actuators and structural metamaterials that can reorient, harden, or reshape themselves depending on the incoming attack. When the AI senses a projectile approaching from a specific angle, it may adjust the armor's orientation to deflect the strike or activate embedded electrical systems that strengthen the material at the point of impact. Some concepts envision armor with embedded explosive layers capable of pushing outward the moment a penetrator contacts the surface, reducing its effectiveness in much the same way explosive reactive armor works today, but with far more precision and less collateral risk. Mobility itself becomes a defensive tool. With AI-assisted maneuvering, a future tank may be able to shift its position by mere centimeters in the split second before a projectile arrives. This micro-evasion capability, driven by predictive modeling, turns the tank into an actively moving target even while appearing stationary to human observers. Slight adjustments to posture or angle can drastically reduce penetration, converting a deadly direct hit into a harmless glancing strike. These evasive maneuvers occur too fast for human drivers to execute, relying entirely on onboard AI for timing and precision. Finally, the tank's defensive intelligence does not operate in isolation. In a networked battlefield, every detected threat, every intercepted projectile, and every electronic anomaly is shared instantly with allied units. This creates a distributed awareness across the armored formation, allowing each tank to benefit from the sensory data of all others. If one vehicle detects an incoming missile, the entire formation can respond accordingly, repositioning or activating countermeasures even before the missile approaches. In this vision, defense becomes an active, intelligent, and nearly autonomous process. Instead of relying on thick armor or brute force, the future tank survives by sensing danger earlier, reacting faster and adapting more precisely than any adversary. These intelligent defensive layers turn the vehicle into a moving fortress of algorithms, sensors, and hyper-responsive mechanisms designed to keep it alive in the most hostile environments imaginable. When all these emerging technologies are combined into a single vision, the result is a radically new kind of armored platform, something far closer to a living, adaptive war machine than a traditional tank. The conceptual model for a tank of 2050 and beyond is not defined by size or weight alone, but by its ability to integrate speed, stealth, intelligence, and overwhelming precision into a unified system. Instead of a 70-ton steel colossus, this future design might weigh closer to 40 or 45 tons, thanks to lightweight nanocomposites and metamaterials. Yet despite the reduced weight, it would deliver firepower and defensive capability far surpassing today's heaviest main battle tanks. The vehicle's silhouette would likely be low, angular, and sleek, emphasizing stealth over intimidation. Adaptive camouflage panels cover the hull, responding instantly to changes in light, weather, and environment. The tank's surface could shift from urban concrete textures to desert hues or woodland shadows without any intervention from the crew. Beneath this skin lies an armor matrix engineered to absorb, disperse, or counter incoming threats dynamically, using nanoalloys, electromagnetic pulses, or metamaterial shaping to neutralize danger before it becomes catastrophic. Propulsion is driven by a hybrid magnetic-electric system capable of silent movement during reconnaissance or ambush operations. When high speed is needed, microturbines activate to flood energy into the magnetic coils, allowing bursts of acceleration far beyond what tracked vehicles can currently achieve. Adaptive tracks or hybrid wheel track mechanisms adjust to terrain automatically, enabling smooth transitions between rubble, sand, waterlogged soil, or icy surfaces. In urban environments, compact dimensions and AI-assisted movement allow the tank to navigate narrow passages and unstable structures with remarkable precision. Armament is centered around a railgun capable of launching hypervelocity rounds that rely purely on kinetic energy. Secondary systems include multi-spectrum laser turrets for anti-drone and anti-munition defense, as well as intelligent micro-missile pods designed for precision strikes in cluttered environments. Internally stored drone swarms provide reconnaissance, electronic warfare, and offensive capability, effectively extending the tank's reach far beyond line of sight. Every weapon integrates with the AI-driven fire control system, allowing seamless coordination across all offensive tools. The true core of this vision, however, is artificial intelligence. The tank functions as a fully networked combat organism, interpreting battlefield data, predicting threats, prioritizing targets, and adjusting tactics with minimal human input. Whether operated by a crew or functioning fully autonomously, the vehicle constantly adapts to new threats, learns from encounters, and updates its internal models. In formations, these tanks share data instantly, creating a distributed intelligence network capable of overwhelming enemy forces through superior coordination and awareness. In essence, the tank of 2050 and beyond is not an incremental improvement. It is a shift in philosophy, a platform that blends stealth, speed, AI-driven insight, and extraordinary firepower into a single entity designed for the unpredictable, multi-dimensional battle spaces of the future. As we reach the end of this exploration into the future of armored warfare, it becomes clear that the next generation of tanks will not simply be more powerful or more heavily armored versions of today's designs. Instead, they will embody a profound shift in how machines interact with the battlefield. Every element we've discussed, adaptive armor, silent propulsion, hypervelocity weaponry, multispectrum sensing, advanced camouflage, and AI-driven autonomy, points toward a future where tanks become dynamic, intelligent systems capable of shaping their environment rather than merely enduring it. This transformation reflects the broader trajectory of military technology, where information, prediction, and flexibility matter just as much as raw strength. The concept of a future tank is not a rigid blueprint, but an evolving idea shaped by the challenges of modern warfare. As drones proliferate, electronic warfare intensifies, and artificial intelligence expands its capabilities, the design priorities of armored vehicles must shift accordingly. The tank of tomorrow must be able to operate in an environment where threats come from every direction, where milliseconds determine survival, and where the ability to remain unseen may be more valuable than the ability to withstand direct hits. It must integrate seamlessly into a network of machines, each sharing data, adjusting tactics, and supporting one another in real time. The future tank is not an isolated combat unit. It is a strategic node within a larger ecosystem of autonomous and semi-autonomous systems. Yet amid these technological leaps, questions remain. How much autonomy will militaries allow machines to have? Will human operators continue to serve inside armored vehicles? Or will remote and fully autonomous platforms dominate future battlefields? How will ethical considerations shape the use of AI-driven weapons? These uncertainties remind us that technology does not evolve in a vacuum. It reflects human choices, doctrines, and values. The future tank may be a marvel of engineering, but its role will ultimately depend on how societies choose to balance capability with control. Even so, one thing is undeniable. The boundaries of what a tank can be are expanding. Concepts once confined to science fiction, Cloaking surfaces, drone swarms, railguns, metamaterials are now inching toward feasibility as research advances. Whether these technologies arrive in 2050, 2100, or beyond, they signal a future where armored warfare is faster, smarter, and more unpredictable than any previous era. The battlefield will no longer be defined by massed metal moving across open ground, but by adaptive machines that combine stealth, intelligence, and precise firepower into fluid, constantly shifting operations. This is all conceptual and speculative. Your ideas matter. Share your thoughts below. If you'd like to explore more future war concepts, you're welcome to subscribe. No pressure. Noen Bing Moon, Mkote.